Hello. Uh, Hello, good evening, one and all. Am I audible to everyone? Please let me know, anyone.
Yes, yes.
Yes, sure.
Yes, yes, yes.
Thank you. Thank you for your response. Uh, Almost like 13, 14 people have joined here. Okay, so as the time is limited, I'm going to start now. Okay, good evening, one and all. Just if anyone is outside from your home, just mute yourself. Uh, please stay safe. I hope all of you are staying safe. Uh, this is Ganesh here again to take the lecture 2. Today's presentation is based on learning design basics, what we are required for design of a PEB structure. Before entering into that, I'm going to discuss just what we have seen in last day's class. So first of all, we have seen in the last lecture PEB definition. What is meant by PEB? How taperization of PEB members will be done according to BMD, and what are the advantages of PEB over an RCC structure or over an uh, conventional steel structure. What are the disadvantages of PEB we have seen? We have compared some RCC structures with PEB structures, and we have seen much more advantages for PEB structure over RCC structures. Uh, but why people are going mostly for RCC structures and India becoming an RCC jungle? Uh, PEB structure is somewhat costlier than an RCC structure for the same area. That's why most of the people are going to choose RCC structure here. And we have seen the different types of PEB structures. We have seen different types like rigid frame structure, BC column, beam column 1, beam column 2, and up to BC 5 or something we can do. And multi-span structures, single slope or monoslope structures we have seen. And what is meant by lean to we have learned, and lean to and single slope, T canopy, L canopy we have seen. And we have seen the different components of a PEB structures like purlins, girts, sheeting, and other accessories like skylights and insulations. Like what are the miscellaneous accessories which making in PEB we have seen in the last class. And different types of loads to be considered. We have seen dead loads, live loads, wind loads, seismic and self-straining loads like temperature, etc. And how the load will be transferred from top to bottom or laterally we have seen through which components it will be transferred. And what are the various tools available for PEB design we have seen like StatPro, ETAPS, MBS, Test, TECLA, etc. And what are the different codes in followed for PEB design in different countries we have seen like US and Indian standards. Uh, because most of the people are well known of Indian standards here and AISC standards, and we have seen some references from where we have taken, and I have given you some assignment for this lecture to move on to the further. So in today's class, we'll see the introduction to design basics. Basically, I think everyone is seeing my screen, right?
Yes.
Yes, okay, fine. Thank you. So every structure has to be designed with some basic regulations to be constructed with some basic regulations in order to maintain safety for a long time. So we can call it as codal provisions. So we have seen some different codes available for PEB design like that. And before going to the design in the next lectures, there are some basic design basics you have to know. You need not to go through the entire code books. That doesn't mean a code book has some unnecessary points. Everything in the code book is a necessary one, but we have to choose the key points or highlight the key points which we are dealing with in the upcoming classes. So generally, I am using here ASE. Someone is. I'm getting someone's noise. Please mute yourself first. I'm requesting you. Okay, fine. Thank you. So I'm going to choose ASCE or AISC because most of the clients in India, nothing but 70 to 80% of the clients is asking to follow AISC design. Since we have a limited time, we have to prioritize the client's requirement and go through it. Fine. So in this lecture, we will see some introduction to design basics. So first of all, codes introduction. What are the codes we are going to use in PEB in the next upcoming lectures? And we have what we have different methodologies as per codes, and what are the load combinations available for different methods, and classification of structures for local buckling. How the sections are classified for local buckling, and effective lengths of compression members like columns we have seen in IS 800 we can see in table 11. So in ASC how we are going to use, we'll see what are the general specification of materials. This is the main important aspect we have to know, like yield strength, etc. You have to know in the general specification of the materials, and we'll go through it now. So these are the codes we use here: AISC 365 or 10. What is meant by an AISC? American Institute of Steel Construction. 360 is nothing but unified. So this is unified American code, which is developed in 2005 and which is modified in 2005 and 2010, and the latest version available here is 16. But most of the people are using 5 and 10, so we are also discussing about these codes. So I think all of you have doubt regarding this one, why we are using 2 years codes here, why we have to discuss 2005 code and 2010 code. Sorry. Someone mute yourself, please. And the next thing, ASCE 705 and 010. This is the minimum design loads what we have to consider for buildings and other structures. This is also modified in 2010. The latest version is 16 here. Yeah. So why we are discussing 5 and 10? What is the difference between ASCE 75 and 710? This is the main important aspect we have to know. Though there are some minor changes, the major changes between ASCE 75 and 710 are the wind speed. In ASCE 75, they have given only one wind map based on basic wind speed, whereas in ASCE 710, they have given 4 wind maps based on ultimate wind speed by using risk categories 1, 2, 3, and 4. So here they have used.
Sir, excuse me, sir.
Yes.
Sir, why Indian code is not available in?
No, Indian code is available, but I have told you we have a limited time. And most of the customers, 70 to 80% of the customers are asking about American, asking about to follow American standards only. That's why I'm going to discuss here. If you want Indian codes, we'll also have discussion on Indian codes also. No problem at all. I'll
Okay.
explain you
Oh, okay.
the design
Sir,
basics for Indian. Yeah.
one more question. We are using American code in India also.
Yes, yes, exactly. That is what I'm telling you. In India also 70 to 80% of the clients are asking to follow ASCE specification only. That is why I am here to discuss about ASCE codes, right?
American code is give a higher steel or lower steel compared to
What do you mean by
ASC
a
or
higher steel or lower
ISC.
steel?
I
Just
means just by weight अगर हम यूज करेंगे ASC और 800 875 जो हमारा इंडियन का है तो दोनों में क्या स्टील कंपैरिजन कैसा आता है कम किस में आता है
because
इकोनॉमिकल कौन सा होगा इकोनॉमिकल
I'm going to answer definitely for sure why people are going for ASE design. For sure, there is some reason in tapering of members. Based on tapering of members, I'm going to clear your doubt soon at the end of this lecture. For sure, why people are using here. In ASE, they'll get more economical design. How they'll get economical design, I'm going to explain you at the end of the class. Just all of you, if you have any doubt, please put your doubt in a paper and we'll have a discussion at the end of the session. Please. Just for a moment, please mute yourself and I'm going to explain your doubts at the end of the session. Please bear with me. Okay, just mute yourself, please. Okay. Just I'm going through this. Wind speed. They have used the term basic wind speed in ASC 75, and they have used the term ultimate wind speed in ASC 710. So, what is the difference between basic wind speed and ultimate wind speed? Basic wind speed is based on one map which have a written period of generally I have mentioned here 50 years if we take importance factor 1, whereas the ultimate wind speed which has a written period of minimum 700 years if we use risk category 2 and 1700 years if we use risk category 3 and 3. So what are these importance factors and what are these risk categories? So importance factor is a factor which introduced in ASC 75 based on the type of structure, whether it is using for residential purpose or hospitalization or general structures or emergency structures. For general
Sir,
structures,
please mute everyone from your side. Please mute everyone from your side. There is a lot of voice coming from your side.
Yes, exactly. That is what I am telling. Someone unmuted themselves. Just I'm muting them. Uh, right. Okay, fine. Hmm. Uh, okay, where we are? Okay, so importance factor, which is introduced in AC 75. Importance factor is based on the type of structure, nothing but the type of purpose of structure, whether it is a general building or emergency building like that. If we use, so if we use importance factor of 1.5, that will give a return period of 100 years. So all of you have generally have doubt what is meant by a return period. I have mentioned here mean recurrence interval. So return period or mean recurrence interval. This is the probability of exceeding the given wind speed. Okay, the probability of exceeding given wind speed. Suppose the customer has given some wind speed like 140 kph or 150 kph, something like that. So the probability is that for every 50 years this may get increased, like that, the probability of getting exceeded. So this is mean recurrence interval we term, or we can call it as return period, wind return period. So this 500 years for importance factor 1 and 100 years for importance factor 1.5 according to ASC 75. Whereas while coming to the ASC 710, they have removed the importance factor. They have introduced a new term, risk category. So risk category is also same like importance factor based on the occupancy category, like school buildings or commercial buildings or marketplaces or some public places, like that. They have divided into the 4 categories, like category 1, 2, 3 and 4. Category 1 is like same thing which we have in AC 75 with 50 years, category 2 700 years. For 3 and 4, wind return period have 1700 years. So if we see probability of annual exceedance, for example, we are constructing with by considering 140 kph speed. So how much probability you have by exceeding wind speed will exceed in this year itself? There is 2% of probability, that is 1 by 50. If you divide 1 with 50, that gives you 2%. So there is 2% of probability. So out of 100%, you will get 2% of probability of annual exceedance of wind speed for every year. Whereas in ASC 710, these have longer return periods. If you divide 1 by 700, there will be some negligible value, that is the lower probability, that is the lower chance of getting wind exceedance according to the ASC 710. But in AC 75 design and in AC 710 design, almost will get the same weight or the same tonnage we can expect in PEB structure. So next thing, different methodologies available according to these codes. One is ASD and 2 is LRFD. I think we have in Indian codes working stress method and limit state method. We have like that, same as working stress method, we have allowable stress design. ASD means allowable stress design or allowable strength design, some may call, that is ASD according to ASC. And the other thing, LRFD, load resistance factor design. Load resistance factor design, LRFD. Like that we have in LSM, limit state method, in IS 800. So what is meant by an allowable stress design? In allowable stress design, the allowable strength will be greater than or equal to the required strength basis on ASD combinations. So the required strength is nothing but, for example, we have to design a particular structure with dead load and live load. The allowable strength must be greater than these loads, right? So allowable strength is defined as Rn by, which is omega. Omega is nothing but allowable stress factor or safety factor, we can call it as safety factor. Rn. So what is Rn here? Rn is nothing but nominal strength of the material. So if you observe this, actually according to the ASD, omega values will be always higher than 1 will be always higher than or equal to 1. So 1 by 1 divided by the value which is more than 1, that gives you 0 point something. So right. So we are reducing the nominal capacity of the material, nothing but we are limiting the nominal capacity of the material in ASD. And whereas in LRFD design, the design strength must be greater than or equal to the required strength. We have seen in ASD, we termed it as allowable strength because we are limiting the material property here. But in LRFD, we are terming it as design strength. We are multiplying one factor with nominal capacity of the material, which should be greater than RU is nothing but required strength according to LRFD combinations. LRFD is nothing but load resistance factor design. Whereas you can see here phi Rn must be greater than or equal to RU. So what is meant by a phi? Phi is the load resistance factor here. So phi values will be always less than 1 if the less than 1 will phi is multiplying here. If the multiplying factor here comes to the other side, it gives you RU by phi, right? For example, phi Rn must be greater than or equal to RU, right? This is our equation. So phi is multiplying here with Rn. So if we take phi on the other side, Rn must be greater than or equal to RU by phi, right? So phi value will be always less than 1 if that is 1 by something which is the value, we are dividing the value with less than 1, that gives you more than 1, right? If the value is less than 1 on the bottom side, you'll get the value which is higher than 1. So RU will be multiplied with a factor which is greater than 1 here. That is nothing but the required strength is nothing but either dead load or live load or wind load or something else which is the load coming onto the structure. We are multiplying it with some value which is higher than 1. So nothing but in LRFD design, we are increasing the loads. In allowable stress design, we are limiting the material property. In LRFD design, we are increasing the loads, right? So this is the basic concept between ASD and LRFD. So if we see these are ASD combinations. So ASD combinations on ASC 7.5 and ASC 7.10. So all these values indicate some D. Suppose let us take what is D here. D indicates dead load, whereas F indicates fluid loads with certain height, whereas H indicates hydrostatic pressure, and L includes a floor live load. There is a difference between a floor live load and roof live load. LR here you can see this is a roof live load, and whereas T here is temperature load or self-straining force we can call, and S or are nothing but snow or rain loads. We generally will not use snow or rain loads here. Generally we use dead load, live load, seismic load, and wind loads and temperature load. So W you can see here, this indicates a wind load. So if you observe here, ASD combinations compared with ASC 710, all the things are similar, but while coming to the wind load, they are using no coefficient for wind load in ASC 7.5, but they are using some 0.6 wind load, right? if you observe, there is a factor for one wind load in ASC 75 and there is factor of 0.6 here. That is nothing but they are reducing the wind load here. Why they are reducing the wind load? As discussed earlier, the ASC 75 is based on basic wind speed, whereas the ASC 710 is based on ultimate wind speed. Ultimate wind speed always higher than basic wind speed. So if you want, I can tell you the factor. Ultimate wind speed will be obtained by using basic wind speed by multiplying with root over 1.6. So you can obtain ultimate wind speed by using basic wind speed multiplied by root over 1.6. So based on this, ultimate wind speed will be always higher than a basic wind speed. So here in ASCV 710, you will get more wind pressure, right? Whereas in ASC 75, you will get less wind pressure. Because it is less wind pressure, they are directly using factor 1 for wind load here, whereas we are getting more wind speed, they are using factor of 0.6 here. Like that you can see, whereas here also wind load factor 1, here they have used 0.6. Nothing but there are no other changes. They have removed some unnecessary loads like fluid load and hydrostatic pressure. H is nothing but hydrostatic pressure, which is in ASC 75 combination. Later they have removed the hydrostatic pressure combination in ASC 710. We can use, generally we don't have hydrostatic pressure except when the structure is located at river banks or etc. So they have removed. If we want to use those hydrostatic pressure in our condition, generally they will be accumulated with D itself. I hope all of you clear about these AC 75 and 710 combinations. The basic difference is in wind only. They have used one wind factor for AC 75. They have used 0.6 wind factor for AC 710. You can also see there is a 0.75 wind here. They have used 0.75 instead of wind. They have used 0.6 wind here. Like that, they have provided combinations. And these are LRFD combinations. So if you observe ASD combinations and LRFD combinations, the factors are the factors in LRFD combinations is always more than 1. Suppose if we take first load combination here, sorry, if we take dead load factor 1 here, in LRFD it is 1.4. So LRFD combinations will use always factors more than 1, because I have just told you the phi value will be less than 1 in LRFD if phi comes to the other side, because that is multiplying by Rn there. If it comes to the other side, the value will be more than 1, right? So 1.4 D here, whereas 1.2 dead load plus 1.6 live load, like that. If we generally there will not be any difference between these two combinations also, 7.5 and 7.10. The basic difference is here you can observe wind. Here they have used 1.6 wind, 1.6 factor for wind combination, and they have used 1 factor for wind combination here. Here also you can observe the factorization will be more here in AC 75 because the wind pressure will be less, whereas the wind pressure will be more in AC 710 and they will use less factor because the design has to be same in any way. Okay, and the other thing, I think someone asked me in the last class, we are designing in elastic analysis or plastic analysis. So for that purpose, generally I'm just using the other slide here. Generally, I think all of you know about this basic stress strain curve. So just I'm writing one here. Oh, sorry. Yeah. All right. Okay, fine. So what is the equation for ASD? Rn by omega should be greater than or equal to Ra, nothing but required strength in allowable stress design, right? If we see, generally in the stress strain curve, the stress will be along y-axis and strain will be along x-axis. So I think all of you know about this. There will be some portion, up to that portion, the stress will be directly proportional to the strain. Generally, we call it as, it will be, Hooke's law will be applicable up to that region. Though there is some portion, strain, stresses that will not be directly proportional to the strain, but that region will be in the elastic region. You can see here, this portion is elastic region, right? Because after that portion, after nothing but at that point, yield strength will occur. After that portion, though there is no increment in load or stress, strain will be increased predominantly. So at that point, yield strength will be plotted. So the last point in the stress diagram is up to elastic region is yield strength, right? So at yield strength generally will denoted by Fi. I think all of you know. Stress is nothing but load by area, P by A. I think all of you know. What is this load? So P is nothing but here Rn. So nothing but nominal strength divided by cross-sectional area. You can find Fi here. So yield stress is based on nominal strength of the material. So this stress strain curve also can be plotted as load displacement curve, whereas load will be on y-axis, displacement will be on x-axis. So in that load displacement curve, Rn will be at this point. If we see ASD, the factor will be, I just told you, the omega will be always greater than 1. So 1 divided by the value which is more than 1, that gives you 0 point something. So that will be less than 1. So the allowable stress will be within the elastic region, right? If we see in LSD also, or LRFD, if we see in LRFD also, we have used phi Rn, which should be greater than Ru. Nothing but LRFD required strength here. So phi value will be always less than 1. I told you. So this is also 0 point something. So here also you'll get LRFD design here. So Rn will be here. Phi Rn means nothing but less than 1 here. And here also it will be less than 1. So which will be well inside the Rn values, right? So we are doing elastic analysis only. There is no doubt we are not using any plastic analysis here, because all the values will be well within the Rn, because all the values will be less than 1 only. Here also less than 1, in ASD also less than 1, right? So next, moving on to the next topic. This is classification of sections based on local buckling. So there are two types, beams and columns. So how the beams can be classified? According to ASC 75, there are three types of sections available. One is compact section, and the second one is non-compact section, and the third one is slender section. So how these compact, non-compact, and slender sections can be categorized? So the compact section can be defined if the beam, this is for hot rolled I sections. I provided you here one table. This is for hot rolled steel of flanges hot rolled steel and flanges built up steel. Before going to the hot rolled and built up and cold formed, the difference between hot rolled, built up, and cold formed you have to learn. So what is meant by a hot rolled section? Hot rolled section is nothing but they'll pour they'll pour the steel, hot steel into a mold, so that they will form a section after the cold process will be done. So like that, they'll cast one section in the mold, that will be called as hot roll steel. Whereas built up section, built up, the term itself indicates that they will build the section by using different plates. Suppose if you see here, this is one flange plate and this is one web plate, and there is the one bottom flange plate. All these plates will be connected to form an I section by using welds at the joints, right? So this section can be called as built up section. If you closely observe, the hot rolled sections will curved, hot rolled sections will have curved edges here, because they will cast in a mold. Whereas they'll in the built up sections, they'll be manufactured by using different plates, right? So they will have sharp edges here. That is the major difference you can observe. And the cold formed section, other one you have to learn. The cold formed section is nothing but is it will be also by taking a plate. So the plate can be tilted or something, bended or something like that. They'll form a separate shape. Suppose a flat plate is here like this, they will bend it by using some machine to form a shape like a purlin or a gut like this. So these are cold formed sections. So basically hot rolled section will be casted in a mold, built up section will be by using different plates joined together, and whereas cold formed sections will be plate bended into the required direction. So for hot rolled I sections and channels, these are the limit. If the value, the calculated value from this formula is within this lambda p, nothing but limiting factor, for compact region, the section can be called as compact section. If the value is in between lambda p and lambda r, the section will be called as non-compact section. If the value is higher than the non-compact slender value lambda r provided here, the section can be called as slender section. Like that for hot rolled sections, for built up sections of flanges, and these are for webs. So for example,
Sir, one question, sir.
Sorry, yes, tell me.
Can you differentiate the compact, non-compact?
Yes, for sure. Basically, these compact, just a minute. Yeah. Basically, these compact, non-compact, and slender sections are based on these parameters only. Though they have not provided any particular definition, we can just understand a compact section will have the practical observation is that the compact section will have wider flanges with lesser depths, whereas the non-compact section have just the flange depth will be just over the the web depth will be just over the flange depth of the flange width of the plate, whereas the slender sections will have the longer webs. You can observe the longer webs with limiting width of the flanges. This is the practical observation. There is no particular theoretical observation in any code book here. They have given these values to identify the type of section. Okay, a compact section will be of the webs will be less than the flanges. The web depth will be less than the flange width. General observation this one. And the non-compact section will have the depths of the webs will just above the flange width of the plate, whereas in slender sections they will use longer web depths. Okay, clear? I think.
Yes, sir. Yes, sir.
Yeah. Okay. Thank you. Sorry, I was about to tell other thing here. Yes. Okay. Okay. For example, if we take an I section with 600 web depth by 5 mm thickness of plate and flange of 200 of width by 8 mm thick flange plate. Okay. For example, how to calculate this lambda p or lambda r values. For example, if we take 600 by 5 web and 200 by 8 flange and I section, how to calculate this? So so first of all, we have to check for compact section whether it is compact section or not. So for that, we have to know E and Fy values of the steel. What is the E value of the steel? E is nothing but elastic modulus of the steel. I think we all have knowledge about elastic modulus, right? The value of elastic modulus for the steel will be 2.05 into 10 to the power of 5, right? Whereas Fy is nothing but the yield stress of the material which we are going to use in a PEB industry. So generally, high yield steels will be used at the PEB industries. For example, in our discussion, let us take grade 50 steel, American AC 572 specification grade 50 steel will have 345 Newton per mm square of yield stress value. Okay, I'm again telling you, we are going to use higher yield strength steel materials in PEB industry. According to AC, the minimum we have to use is grade 50 steel, nothing but 50 KSI, kilo pascals per square inch, nothing but in Newton per mm square, we can tell it as 345. So E by Fy, that is 2.05 into 10 to the power of 5 divided by 345, square root of this one, which gives you 24.38, right? So I have calculated a value of E by square root of E by Fy. So that is 24.38, right? So 24.38, 0.38 into, first we have to check it for compact section, whether it is compact section or non-compact. First we have to check for compact section check. So 0.8 into 24.38, that gives you 9.27. So this is 9.27. Just a minute, I'll mention here. .27, and this is 24.38 for sorry, this is for hot roll section, I think. Yes, these are for built up. So this is 9.27 here, whereas okay, so they have used some Kc factor here and FL here. So what is this meant by Kc? They have given some formula for Kc here. Kc is nothing but 4 by root over h by Tw. So here they have used one value for Kc. Kc is nothing but 4 by root over h by Tw. So this h is nothing but the depth of the web and Tw is nothing but thickness of the web. What is h by Tw? So h by Tw value will be 600 by 5, right? 600 by 5. This gives you 120. So root over 120 gives you 10.95. 4 divided by 10.95, which gives you 0.36. So, right? So 0.36 into E by FL. We all have seen Fy here, but what is meant by an FL? This is limiting factor for yield strength. FL is nothing but 0.7 of Fy. The code have provided all the values here. No need to worry about this. So 0.7 of Fy. So Fy is nothing but all of you know. I'm going to use here 345 grade steel. So Fy is 345. 0.7 into 345, which gives you 241.5. So now we calculate this lambda R value here, right? So we have a Kc value here, that is 0.36 into E value 2.05 into 10 to the power of 5 divided by FL. FL is here. FL is nothing but 0.7 Fy you have seen just now. That is 241.5. This is the value. We have to square root it so that it gives you 17.48 something. So 0.95 into 17.48. That gives you 16.06, right? Here you have got a value of 16.06. So here we have to check B by T. B by T is nothing but BF by 2, nothing but the overall width of the flange divided by 2. Here we are going to use 200 by 8 thick flange. So 200 by 2 is nothing but B is equals to 100 only, right? So B by T is nothing but 100 by 8. T is nothing but thickness of the flange (100 divided by 8), which gives you 12.5. So 9.27 is the limit for compact section. 16.08 is the limit for non-compact section for B by T value. But what we have got here is 12.5 value, which is exceeding the compact section limit, so that we are using here as this is non-compact section. So 600 by 5 by 200 by 8 is a non-compact section. That is how we have to calculate the lambda p and lambda r values based on the section properties, and how to find the type of the section. I think everyone is clear, right? So for similarly webs also, here h is nothing but height of the web, whereas PW is nothing but thickness of the web. These are the values for compact section and non-compact section. So basically, generally in the PEB industry, most of the PEB manufacturers are going to use slender sections or non-compact sections only. They'll less use compact sections, because the slender sections and non-compact sections are more economical, because the web depth in these sections will be more when compared to the flange width of the I sections. That gives you more economical section, right? So that is why most of the PEB industry manufacturers are going to use non-compact and slender sections mostly.
Sir, one question, sir, here.
Yes, tell me.
There is a limit for slenderness also, no? Like, for example, sometimes in STAT it will show.
Yes, for sure. For example, KL by R or slenderness ratio will be limited to 180. In some cases, for flexural cases, for tension cases, we'll use it to 200 according to ASC. Yes, they'll use for sure. This is the slenderness check, and we'll discuss all these checks in design parameters of the STAT. Next class, we are going to learn some design parameters where the slenderness checks will be there, and we'll see all these values. What are the value of slenderness, maximum slenderness value? That is also we have to check, because the structure the structure should not collapse, right? So we have to check slenderness also.
Yes, sir. Here the slender, whatever the section we are selecting, slender or non-compact, should not exceed, you mean 180 or 200?
Yes, exactly. I will tell you, for flexure it will be there will be some different value. For tension there will be different value, and for compression there will be different value. There will be some different values for different types of components. We'll see all this.
Sure, sir. Sorry for interruption.
Fine. So all these are for beams we have seen here, and the next one you will see columns. For columns also there are slenderness ratios we have, but according to AISC specifications, columns are defined only two types. There is non-slender column or slender column. This is the lambda value they have given. If the lambda value of or the B by T value is less than this lambda value, you can decide it as non-slender section. If it is more than one, you can decide it as slender section. These are for hot rolled I sections, and these are for built up I sections. So I have told you what is meant by a hot rolled and what is meant by a built up section. And the most important one you have to know in the design is nothing but effective length factors for compression members or columns. there is no effective length factor for rafter in AIC code, but we have to know what is the effective length factor for a column here. Generally, we have, I think, in table number 11, right? In IS 800, in table number 11, it is there for a column. So here, table CA71 in ASC 7, AISC 365, you can observe table CA71. These are effective length factor for columns. So yes, this is the first. If you see first case, the column base is fixed, nothing but there is no movement allowed, there is no translation allowed, there is no rotation allowed, nothing but no movement, no movement released, movement is not released here. So rotation is fixed and translation is fixed. It is completely of fixed support. Here also there is completely fixed support. For that, there is theoretical value and recommended value to be used in design. But in PEB, all we are using are sway frames. Definitely, if you fix here also, there will be some sway like this, right? Due to wind pressure or something, any other loads, there will be some particular sway. So always there will not be any fixity here. Completely, there will not be any fixity, right? Always we are going to use sway frames. That's why ASC they have given deflection limits also. So nothing but we are going to use sway frames. There should be some definitely sway. So this condition will not applicable in our PEB section. And this is the other thing. This is the one case generally occurs. The top section is pinned here. The top section is pinned here, nothing but if we take a column, if we take a frame like this, suppose if we take an end wall frame. So what is meant by an end wall frame? I'll let you know in the next class. All these end wall frames, bay frames, what are these bay frames? I'll let you know. Suppose for time being, let us take this as an end frame. The condition here is bottom is fixed and top is released. Here this is the condition. But generally for any wind column, we will not use bottom as fixed condition. So this case also not applicable. Generally, general cases I'm talking about. So generally this case also not applicable here. But these are the 4 cases which are applicable in regular PEB buildings. So this is the first case I have told you. For a rigid frame, we have a fixed base with a fixed base. Generally, for any frame, we have to check for pinned base only, first of all, because pinned base will give you more economical footing, right? Also, we can taper the sections for columns, but in fixed base, there will be huge footing and we cannot use tapered section because the moment diagram will be, I think, for fixed column, how the moment will be there. Here like there will be some fixed moment and there will be some negative moment and there will be some positive moment. So how you can taper a section for a moment like this? But for a pinned base, if it is pinned base, the moment diagram will be always like this, right? Because at the pinned moment will be 0, at the partially fixed and the moment will be much more compared than this pinned end, right? So you can taper section like this, but in fixed case, we cannot the taper section. We cannot do the taper section. That's why generally we have to check any building for pinned base only. If there is no controlling sway in pinned base, then we have to go for fixed base. So in that case, this case will be applicable. So the theoretical value for effective length factor is 1, but practically we will use 1.2 here in design. In the second case, just I have told you, this is the wind column case. Pinned is fixed and top we have to fix because the column will be rotated. Why the column will be rotated, I will tell you. So this is the second case we are going to use in our PEB. There is only factor of 1 for a wind columns. The top is pinned and the bottom is pinned, nothing but rotation is allowed at the both ends, but there is no translation allowed. So this is for free and at the top portion and fixed at the base. That nothing but we have seen some L canopy, T canopies we have seen, right? For that portions it will be applicable. And the other thing is for a pinned base column. Just now I have told you we can use tapered section for pinned base columns here. For that cases we will use effective length factor of 2, but practically this has modified in recent days. We can use just 1.5 only. Okay, in case of 2 we can use 1.5 only based on some recent researches. You know, code has not just updated, but based on some researches we can use 1.5 only. This is the practically used effective length factors in nowadays. Is there any doubt regarding these sections? Only just we are going to use we are going to use these 4 sections only in our PEB sections right now. These 2 are not applicable because we generally use sway frames. This is for non-sway frame. There is no frame without sway in the PEB. There will be some certain sway, but that should be limited in order to safety, right? This is non-sway frames. We are not going to use this. And for wind columns, we will not fix base for rare conditions. So this is also we will not use. So except these 2 cases, these are the 4 cases we will use. In this, generally, we will use instead of 2, latest recommendations are 1.5. Sorry. This is 1.5 only. So these are the general specifications of the hot rolled materials which I am going to explain you in my design. This is generally primary steel hot rolled sections are ASTM A36. What is meant by an ASTM? American Society for Testing of Materials, ASTM, A36 grade. 36, what is meant by this 36? 36,000 PSI I have mentioned here, right? Pascals per square inch, sorry, pounds per square inch, whereas you can say 36 KSI, kilopounds per square inch. So basically this is based on American codes. That's why they'll generally use pounds, etc. In our India, we generally use metric units, right? Not this one. So ASTM A36 grade for primary steel hot roll members and primary steel for built up members grade 50, nothing but 50 KSI. That is 345 MPa. Just I have told you while calculating the type of sections. I told you like this, right? This is FI 345, and for cold form steel also, by using these plates only, they will mold required shapes, channels or G sections, or channels with lips or without lips. So they'll mold. So these are the general specifications of the material. FI is 250 for hot rolled members, 345 for built up and cold formed members. Generally, we will use in our design. If you go to any particular company, there may be different. But I'm just telling you my experience here. After you go through a company, they will tell you what is the type of material they are using. Okay, For the learning purpose, I am taking these are default values. Yes. So I think so I have told just there are two methodologies available, ASD and LRFD, right? So, sir, in this method, do you have any doubt regarding using this method? When we will use ASD, when we will use LRFD? So the basic is that in ASD, generally, if the live load to dead load ratio is greater than 3, generally ASD, nothing but allowable stress design, will give lighter section, that is economical section. If live load to dead load ratio is less than or equal to 3, LRFD design will give you slightly economical section than ASD. This is the main important aspect you have to know. We can use both ASD design and LRFD design. If the live load to dead load ratio is nothing but generally live load will be 0.5 to 1 on an average. If you take generally 0.6, if the dead load is 0.1 or 1.5, so live load to dead load ratio 0.6 by 0.15. So how much it will be? 0.6 by 0.15, that gives you 4. So this is greater than 3. In this case, we can use ASD method of design, allowable stress design. If this is not happened, if it is less than 3, we can use LRFD design. So these are the references I have taken. I have just added one more reference from the last one, design guide 25, frame design using web tapered members. You can also browse this design guide 25 and you can check whether you can gain some more knowledge about how tapering will be done in this manual. This is design guide 25. This is approved by AISC. So you can just browse and go through it, AISC design guide 25, right? Any other thing you want to know, just share your doubts if you have. Sorry, yes, there are some doubts you have mentioned here. Indian code, I have told you. What about Indian code? Yes, most of the cases are why not Indian code? Yes, I have just told you. I will tell you Indian code, Indian code design specifications for sure. Just first let me complete this AISC design and then I'll go through the Indian code design. There will be no change at all except load combinations and methodology and wind load cases. So I'll explain you. And this IS 875, no sir, what we are not satisfied. Why were we not design was not based on sure, the design I will explain you in IS code also. Yes, MBR followed. Yes, maximum AISC. This is the one I'm telling you. 80%, 70 to 80% of the customers are following AISC and MBA. Even though, just one more thing I want to tell you, if the civil engineering harem, this PEB has much more scope in Arab countries like UAE, etc. You can you have to use American code and MBMA recommendations only there. You will not be able to use IS code there. Based on the conditions only, I'm telling you this. If you want IS code, I will tell Indian code only. Wind का इंडिया से क्या लेना है? No, the wind speed only will be taken from IS 875 wind map. and then design procedure will be from AISC design. Yes. Which is more advantage, ASD or LRFD? Just now I have told you, ASD design, if the live load to dead load ratio is greater than 3, we can go for ASD. Dead load, live load to dead load ratio is less than or equal to 3, we can go to LRFD. Yeah, section. Yes, sir. But in fixed base section will be more economical. What do you mean by? Probably you are talking about the column. Okay, fine. In fixed base section will be more economical. In some cases it will be yes. In some cases it will be no. Because in fixed base we cannot use tapered section because the bending moment will be maximum. Bending moment will be positive at the bottom and then it will go to negative and then again it will be positive at the top. We cannot taper section like that, right? So that's why we have to use a straight section, which may be economical sometimes, but most of the cases it will be uneconomical. No, but in sway frame value of K varies from. This is effective length factor. We have to use whatever the effective length factors mentioned in AISC 360. We have to use that one only. So yes, Indian code recommends to use LSM only, but in our cases, working strength method also we are following, right? You are not familiar with AISC code. That's why I am here. I am introducing AISC code because civil engineering has a much more scope in Arab countries. In nowadays, India is also using PEB buildings. Just now I have told you this one, right? America की win का India से क्या लेना? No. In just now I told you IS 875 part 3. There is wind loads specification. We have to take wind speed from that code only, but methodology will be followed by American code. No, what if I use ASD instead of LRFD? Dead load, yeah, you can use, but you will get slightly uneconomical section. There will not be any much more difference. You will get slightly uneconomical section. That is no problem at all. You can use. Yes, this is the general question. When we use ASD, when we use LRFD, generally American code also American code also imposes to use LRFD only because I just shown you the wind load combination, the load combinations, all the factors are much more greater than 1. You can observe, right? So in case of any their future accidental loading, it will come, they can carry. That's why American code recommends to use LRFD only. But for some cases, economical design, ASD also recommended. No problem at all. Yes. Pinned base, which gives economical footing. No, in any steel structure, pinned base will give economical footing. Yes, temperature load combinations also there. You can see. If PEB evotic crane, then what is the base support condition? No problem at all. If crane is also there, we have to check for pinned base condition only. If the sway is not controlled, we have to go for fixed base. Yes, that is the end of the session. Is there anyone?
Hello. Hello.
Yes.
Sir, you were explaining about compact section and cylinder section.
Yeah.
There was a ratio B upon T.
Yeah, B by T. Yeah.
B by T.
Yeah.
That is only for the plate thick. We are checking here only the class of plates, right?
Yeah.
scale upon R about a whole section, right? Like
Yes, exactly.
I'm getting right?
Yes, exactly. The one thing I have to tell you, for generally for flanges and webs, if any, for example, if we are checking for compact section here, any suppose if the flange is in compact but web is in non-compact, we have to take the critical one. The section can be called as non-compact only.
Okay, someone was asking there what is the difference between that and this. That's why I mentioned here.
Did you understand?
Yeah, I got it.
Yes. If the flange is
I
in
want
compact,
I want to mention one more thing. There is so many people that is asking about Indian code and American code.
yeah.
Parameter is limited in STAT. I am right?
Which one? Just
when we assign the parameters in STAT as per Indian code.
Yes.
Parameters are limited.
Yes, exactly. That is what I'm going to discuss in STAT design parameters session is there, no? That at the time I will discuss all about the design parameters.
Yes, sir.
Yes.
Okay.
Okay. Is there any other thing?
Thank you.
Yes, Mr. Srinivas. Hello, Srinivas.
Sir, one question, sir.
Yes, exactly.
Yeah. If you have a crane capacity of 15 tons, can I
How
use
much? How much?
15 tons, sir. 15 ton capacity.
15 metric ton capacity. Okay, fine. Yes, tell me.
Can I use a stepped column or a straight column with a bracket?
Yes, exactly. For up to 15 meters, it is okay to use bracket. Yes, for a 15 metric ton, it is okay to use brackets, but the bracing will be angular. Better to give. They will not take generally for 15 metric ton. They will not give angular. Rod bracings. Generally, we will not use any cable bracings in the cranes if the cranes is present, but we have to use rod bracings for up to 15 metric ton only. If from 15 to maybe 30, we can use angular bracings. More than that, we have to use portal bracings only. Up to 15 metric ton, we can use brackets itself. There will not be need of any stepped column. More than 15 meters, we have to go for stepped column.
It's like a straight column with a bracket with pipe bracing we have given.
Sorry, I didn't get you.
Straight column with a bracket, sir. And
yes, up to 15 metric ton, it is okay.
Yeah. For instead of rod bracing, I provided tube bracing.
Tube bracing is okay, but we should not use rod bracing, which has a much lesser axial capacity, right? Yes.
Sir, one more question. When we apply the load of a crane, what will be the weight difference in per square meter?
Sorry, that depends on capacity of the crane and the type of the crane. If you use,
I am asking a simple difference between a normal shed and if there is any kind of crane.
Yes, generally that depends on the capacity. How much you expect the capacity of the crane? Just tell me.
10 ton. Sir.
For example, if we take 10 metric ton, generally for a 30-meter building, suppose if we take 30-meter width building, there may be for RF with the normal loads, there will not be any dead loads. For example, we can expect 27 to 28 kg per meter square, right? For crane, we can use up to 32 kg per meter square, maybe.
It means there will be 4 kg difference, right?
Maybe, yes, because
up to 4 kg.
Yes, if there is no crab lateral forces, etc. If there is any crab lateral forces are there, just there will not be there will be an increment of 40%, etc. something for crab moving forces. Then we have to control the sway. In that case, we may have to go for fixed base.
Sir, one more question. When we assign the pin base at column and fixed base, I face some problem there.
What is the problem?
I am unable to control the sway of frame.
Why? You can control itself, no? Right?
When we do apply the wind load, sway load is very much exceeding, as per given criteria. It is going about like my column height is about 6 meter and 6.5 meter. Value is
That's
coming
very
about
nominal. No problem.
value is coming about 120 mm.
No. There may be some mistake. We have to check. There may be some mistake. For 6 meter, there will not be much sway like that with the nominal loads.
Sir, how do we control that?
No, by using the by large sections at the haunch portion, generally we can control.
Sir, we do use generally pirated software.
Yes, exactly. Just
is there any?
I recommend not to use pirated sections because
so
there
that's
may
why
be,
that's why I'm
if
asking
you use licensed software, you may your sections may be passed, but in the pirated software, your sections may get failed.
Sir, that's why I'm asking. Is there any manual check? Cross check our section for pirated software.
There will not be any deflection change. No, section unity ratios will change, but there will not be any change in the deflection. No, not at all.
Okay.
Because those are primary load cases only. No, we have to check deflection for primary load cases only.
Yeah, serviceability load cases it should.
Yes, exactly. But you can observe
those will be lesser than the limit that collapse values.
What you are telling?
Those will be lesser than the collapse limited state of collapse. Lesser, so there might be load combination problem.
Yes, if you do not have, suppose if you are going, if you are using LRFD combinations, right? But there is no ASD combinations in your STAD input file. You can check it manually by using primary wind cases only. He is asking for manual check, no?
That is I was asking about manual.
Yes, you can use it for primary load cases. You can check it from primary load cases, each and every component, right?
Okay, sir. Thank you.
Okay. I think everything is over, right?
One more question, sir.
Yes, tell me, please.
Yeah, right now in the Dubai areas, most of the structures like steel structure, like a PEB structure.
Yes, exactly.
Nowadays, the Dubai government is like what I call apply the most of the solar.
Yeah.
So they're erecting a lot.
Yes, exactly. The key point. This is the main point. The solar panel load. Generally, solar panel will come additional dead load here, like.
Yeah.
Right?
So in that case, most of the subjects like the contractor, they are asking for the feasibility study for the existing structure.
Sorry.
So for the feasibility study.
Yes, they can directly use solar panel load in the existing structures. There will not be any check needed because solar panels load will be checked with wind load only. There will not be live load case at that time, right? Generally, if there is solar panel, there will be no live load because live load we take generally for maintenance. If a person goes over the roof, that can compute as live load. If the solar panel is over there, how a man can go, right? So it will replace live load, right?
Yeah, it is replaced within the live load, like a point.
Yes, exactly. You can use directly.
So solar comes like a 0.1.
Yes, exactly. 0.1 to 0.2 there may be, but we are taking generally 0.6 of live load, so it is well within the limit.
Yeah, so it's within the limit. The thing is that the contractors asking for the feasibility study for the existing structure, like a Perlin, Raptor. Those members are paused or failed to putting the additional load of solar. The thing is,
no problem.
The age of the structure is 20 years back. Right now, if we are applying we don't have any detail about the existing structure. Like we don't have any approved right. Which code is they following, like LRFD or ES. If we are apply the additional load of solar, then definitely the member is failed. So in that case, we are recommending for the rectification, like strengthening of member.
Yes,
so
exactly.
in your experience, what kind of strengthening is trace on the existing member, like how you carry on the strengthening of the.
Yes, definitely. We can use nested purlins. In that case, we can use nested purlins. Generally, frames will not fail. But you are asking about some additional dead load coming onto the structure. There may be purlins in case, right? We can use nested purlins over there. Generally, just you can purlins are jet sections, right? You can use nested purlins directly. I just told you in the introduction class itself, you can directly rest a purlin on one purlin. So you can use nested purlins over there at that section only. You can try, no problem.
So, is there any recommendation on strengthening the structure, like to increase the thickness of flange or web by welding something like that?
No, there is no need of any increase in the section of the frame. Just I'm telling you, it will replace the live load. We are designing for the live load of 60 kg per meter square, whereas solar will be of 15 to 20 only.
Yeah, that is okay. But people are, this collateral load nowadays, before while we are designing the structure, they're considering the collateral load like 0.2, 0.3, like that. After the so many modifications, the collateral load will be increased, like a false ceiling, they made some false ceiling. So we cannot accommodate this solar load. The complete entire existing structure is failed, showing the failed while we are analyzing. Yeah, this is the problem we are facing right now.
Surely, I'll let you know in the next class. Okay, any feasibility study we can do. Surely, for sure.
Please. Yeah, please.
Yes, sure. Okay, sir. Thank you. So this is the end of the session. Just okay. Thank you, one and all, for bearing with me. Thank you.